Hey everyone, welcome to today's Explainer. We're about to take a seriously microscopic journey into the fundamental building blocks of literally all matter. We're going to zoom in way, way beyond what the human eye can see to unlock some of the coolest secrets of the universe. Okay, let's ground this in reality for a second. Think about two super common metals, like gold and iron. Gold is shiny, it's completely unreactive, and it'll stay pristine for millennia. But iron easily rusts away into these flaky orange pieces. So what makes them so fundamentally different? Well, the answer actually lies entirely in the invisible, microscopic particles making up those materials. Section 1. The building blocks. So what actually makes up matter? The answer is atoms. They're the absolute smallest particles that still hold the unique chemical characteristics of an element. Now, for the longest time, the atom, which comes from the Greek word atomos, meaning unsplittable, was pretty much just a theory. I mean, they are unimaginably small. But modern science has come so far that we can actually see them now. Just look at this electron micrograph. It's showing actual atoms captured using an incredibly powerful electron microscope. It's kind of mind-blowing when you think about it. Section 2. Meet the subatomic particles. Atoms are actually made up of even smaller pieces that dictate exactly how every single element behaves. Zooming inside, we meet three main subatomic characters. First up, the positive protons, which carry a relative electrical charge of +1 and a relative mass of 1. Next, we have the neutrons. As the name suggests, they're electrically neutral, but they pack that same relative mass of 1. And finally, the electrons. These tiny, negatively charged particles with a mass so incredibly small it's basically negligible, and they just like to hang out far away from the others. Now, these particles follow a very strict organization. The heavy protons and those neutral neutrons cluster tightly together into a super dense, heavy core right at the very center, which we call the nucleus. Collectively, they're known as nucleons. They take up just a minuscule amount of volume, but they actually contain almost all of the atom's mass. But what about the electrons? Well, while the heavy nucleons are chilling in the center, the tiny, negatively charged electrons are in constant, rapid motion. They're basically zooming around the nucleus at specific distances, forming what we call electron shells. And they stay locked in these orbits thanks to a really strong electrostatic attraction to that positive nucleus. Section 3. The astonishing atomic scale. Let's talk about the vast, hidden distances here, starting with mass. To put this into perspective, at a fraction of 1 over 1840, it takes roughly 1840 electrons just to equal the mass of one single proton. Their mass is so exceptionally tiny that chemists consider it virtually negligible. It practically doesn't even count. And when it comes to distance, the scale is equally staggering. The radius of the entire atom, reaching all the way out to those furthest electrons, is about 100,000 times larger than its central nucleus. Okay, here's a fun analogy to help visualize this scale. Imagine we magnified an atom so that the protons became the size of footballs. The closest electrons wouldn't just be nearby, they would be the size of tiny little full stops located 5 kilometers away. That's roughly 50 football fields. What this reveals is an absolutely incredible fact of nature. An atom is almost entirely empty space. Crazy, right? Section 4. Decoding the numbers. So how do chemists actually identify these atoms? They use two absolutely vital numbers. First is the proton number, or Z. This acts as the atom's unique ID card. No two elements share the same proton number. Then there's the mass number, or A, which is simply the total count of those heavy particles, the protons plus the neutrons, packed tightly into the nucleus. Armed with these two numbers, you can determine any atom's exact makeup, because the mass number, A, is your protons plus your neutrons, and the proton number, Z, is just your protons. Finding the neutrons is super simple. You literally just subtract Z from A. Whatever is left over, that's your exact number of neutrons. Section 5. Reading nuclide notation. Now, nobody wants to write all these numbers out in longhand every single time. So chemists use this universal shorthand called standard nuclide notation. You get a large central symbol, we'll call it X here, that tells you the element. The mass number, A, sits up on the top left. The proton number, Z, sits right below it on the bottom left. It's basically everything you need to know about a nucleus, all at a single glance. Let's put this into practice and look at carbon-12. The big symbol in the middle is C. The bottom number is 6, which tells us it has exactly 6 protons, And just a quick reminder, to remain electrically neutral, that also means it has 6 electrons. The top mass number is 12, so subtracting those 6 protons from the mass of 12 leaves us with exactly 6 neutrons. 6 protons, 6 electrons, 6 neutrons, all perfectly represented right there. And that brings us to the end of our microscopic journey today. We've explored the atomic building blocks and decoded their universal shorthand. But before we wrap up, consider this final mind-bending thought. If the atoms making up your chair, your screen, and, well, your very own body are almost entirely empty space, how solid are you, really? Something to chew on. Thanks so much for joining this